Hey guys, welcome to Pre-Calc lesson 8A.3 exponential function applications. Before we get to the applications, let's practice simplifying some of these expressions. Question number 1, I want to deal with each one of these individually because not all bases are the same. So 4 to the 3/2 power, if you recall, is the same thing as saying square root 4 cubed times 16 to the negative 5/4. The negative takes the reciprocal of the base. I'm going to take the 4th root of 16 and take that to the 5th power, and then I have times 4. Square root of 4 is 2. 2 cubed is 8. So this is 8 times the 4th root of 16 is 2, and 2 to the 5th is 32. So that's 1 over 32 times 4. Well, if you notice here, you multiply straight across, you get 32 over 32. So that expression just simplifies to 1. Question number 2, my approach, it's not the only approach. I prefer to move all my negative exponents first to make this a little bit simpler. So in doing so, b to the negative 4 goes to the denominator as b to the 4th. A to the negative 3 goes to the denominator as a cubed. B to the negative 7th in the denominator goes to the numerator as b to the 7th. And c to the negative 2 goes to the numerator as c squared. Now what I would do is multiply everything in the numerator, then multiply everything in the denominator, and then simplify. Like I said, it's not the only approach. It's just my workflow. So 8 times negative 10 is negative 80. I have a to the 6th, and I don't see another a, so a to the 6th. I have c times c squared, so that gives me c to the 4th. And I forgot my b. Over here I have b squared times b to the 7th, so that's b to the 9th. My denominator is 24. A to the 5th times a cubed is a to the 8th. And I have b to the 4th and just b to the 4th. Now this is much easier for me visually to simplify. I have to figure out what number goes into both 80 and 24. I believe that's 8. So I'll divide both of those by an 8. And that gives me a negative 10 and a 3. With my a's, those 6 a's will cancel with 6 of those. So that would just be a squared in the denominator. I've got b to the 9th in the numerator. I've got b to the 4th in the denominator. So we subtract those exponents, you get b to the 5th in the numerator. And then you have a c to the 4th up top as well. So there is your simplified expression. And lastly on this page, I've got some fractional exponents. A couple different approaches here. One thing you can do, those of you that just like to use the rules, think to yourself, okay, this is division. I'm going to subtract exponents. So I want to write it out subtracting my exponents. So you'd get something that looks like this. X to the 7/4 minus 3/4. Y to the negative 5/3 minus 1/3, z to the 1 minus a negative 2. Okay, so if you approach it that way, all our denominators in each term are the same, so I don't need to get common denominators. 7/4 minus 3/4 is 4/4, so that's x to the 4/4. Y, negative 5/3 minus 1/3 is negative 6/3. And 1 minus a negative 2 is 3. So then we just have to do a little simplifying here. Obviously, this is a 1, and this is a negative 2. So one way you can leave this is x, y to the negative 2, z cubed. Or, if you don't like dealing with that negative exponent, because the directions don't specify. On a quiz or an exam, it'll specify don't leave any negative exponents, or don't leave any fractions, in which case you would want the negative exponents. But this answer right here is equivalent to xz cubed over y squared. All right, let's get to our applications. Our exponential equation, a of t equals ab to the t. So notice it's very similar to what we've been dealing with, y equals ab to the x, right? If we're just talking about the coordinate plane. This and that represent the same things they do on the coordinate plane. A represents our initial value. Okay, it'll end up being our y-intercept, if you remember that from the last lesson. B represents what we call the common ratio, or sometimes it's known as a growth or decay factor, depending on if that's more or less than 1. So if B is greater than 1, then the function is increasing or growing. If B is less than 1, then the function is decreasing, or we say decaying. T represents a unit of time. Right? For our real-world applications, we're always talking about time. Could be years, could be days, hours, minutes, whatever the application specifies. And A of T represents the end amount. How much you're left with after T units of time. So here's a simple example from Algebra 1. Judy's looking to purchase a car. The function f of t equals 8,500 times 0.7 to the t represents what the car is worth t years after Judy purchases it. What is the initial value? Well, pretty straightforward. We say that's the initial value, so 8,500. What is the common ratio? So the common ratio itself is simply 0.7. Is this a growth or decay situation? Why? It is decay because R is less than 1. What is the value after 5 years? So we're going to plug this into our calculator. F of 5 will equal 8,500 times 0.7 to the 5th. Obviously, this is calculator active. Let me check what I got there. I got $1,428.60. Now, here's the tricky part. Which of the following is true about the value of Judy's car? So remember this right here. Judy's car's value is increasing by 70% per year. Well, we already said it's decay, so anything that involves increasing, I know is not true. So here's the question. Is the car's value decreasing by 70% per year, or is it decreasing by 30% per year? Well, remember what this means. That is how much remains after 1 unit of time. So 0.7 is the same as 70%. So 70% remains, which means 30% left. So what's happening here is that is a 30% decrease. So it's important to understand what that common ratio tells us. It gives us the amount that remains. Okay, so let's keep that in mind. Percent increase, decrease, and the common ratio. So there's a lot of formulas. You might have learned how to do like this grid or box in Algebra 1, but we really want to kind of rely on number sense. A percent increase, B equals 1 plus your percent increase. Remember, B is that common ratio. So B would have to be greater than 1 in that case. So if you're increasing, if you're growing, that growth factor has to be more than 1, right? Because you're multiplying by a number more than 1, which means you get bigger. A percent decrease, B equals 1 minus the percent decrease. So in that case, B will be less than 1. You are decaying if your growth factor is less than 1. It becomes a decay factor, if you will, because you're multiplying by a number less than 1, so you shrink, you get smaller. Okay, so let's just apply that, write some equations here. Write the equation for each of the following. An initial value of 9,250 increasing in value by 12% annually. So once I see this increasing in value, I know I'm dealing with a 1 plus situation for my B term. 12% is simply 0.12. So when I see this, B equals 1 plus 0.12. So let's do A of t, function notation. Initial value is 9,250. Your common ratio will be 1.12 to the t. 650 people changing by a factor of 5/4. Now notice they don't give you a percent increase or decrease here. They actually give you the factor, the ratio. So in this case, B equals 5/4. There's nothing to add or subtract from. So A of t equals 650 times 5/4 to the t. If you want to convert that to decimal, go ahead, be my guest, but you don't need to. 125,000 decreasing by 3.5%. And this is probably the example that gets missed more than anything else. Percent decrease is always challenging because you have to think about it. You don't just put in the 0.035. When I see this decreasing, my B value is 1 minus 0.035. So you actually would have to calculate that ahead of time. 1 minus 0.035, so that is going to be 0.965. That is your decay factor. Your equation then would be A of t equals 125,000 times 0.965 to the t. Only 3.5% leaves, so 96.5% remains, and that's what goes in your B term. 3.5 million people decreasing by 1/3 each year. So again, that is not the percent, but you're decreasing by 1/3. So let's think about this for a second. If we decrease by 1/3, what remains? 1 minus 1/3, or 2/3. So this function would be A of t equals 3.5 mil. Well, let me just do it this way. Times 2/3 to the t. All right, I just want to mention this. When you see this in words, when you're writing a function, you have to actually write out the number. Don't write in 3.5 million here. Okay, just put the actual number. Okay, moving on. If Rafael places $25,000 into an account and it grows 1.5 times each year, so again, grows 1.5 times. So before I even go any further, my B term is 1.5. Right, an equation can be used to determine how much money Rafa has in his account at any given year. Okay, so let's do this. A of t starts with 25,000. My growth factor is 1.5 and t. Great. How much money does Rafa have in his account at the end of 7 years? Well, we're just plugging in a 7. A to the 7 is 25,000 times 1.5 to the 7th. That's obviously calculator active. Let's see what that is. Looks like $427,148.44. What is the percent increase each year? So my percent increase is B minus 1. How much above 100% are you? So if you convert 100% to a decimal, it's just 1. So this is going to be 1.5 minus 1, which is 0.5. And 0.5 equals 50%. So it's a 50% increase. All right, find the equation of the exponential function modeled in the table given below. So we actually did this in the last lesson. It looks a little bit different here because I give you a table. So in the last lesson, I gave you 2 coordinates. One of those happened to be on the y-axis, so you knew what your A value was. Well, year 0, you're 50,000. So there's your initial amount, or A equals 50,000. So now you have an option. You can pick any of the remaining points as your X and your Y. So I could pick this one, or that one, or that one. I'm going to stick here because that's the easiest one. So remember, X is 1, Y is 35,000. So let's plug into that equation. The Y value, 35,000, equals A, 50,000, times B, which we don't know, to the X or the T, that's just 1. So all we have to do here is divide by 50,000, and B equals 0.7. So Find the equation of the exponential function. Let's do something like this. A of t equals your a value, 50,000, times your common ratio, 0.7 to the t. If you want to use y equals something to the x, that's fine as well. I just did it in function notation. What percent was the balance increasing or decreasing by? So your percent decrease equals 1 minus b. So in this case, it's going to be 1 minus 0.7, 0.3. So 0.3 is a 30% decrease. So it's very important that you guys know how to find your percent decrease. It's 1 minus b versus your percent increase, which is b minus 1. Basically, just remember, how far are you from 1? Never use what's in the parentheses. Never use this. Always ask yourself, how far is this from 1? Well, 0.5. Well, there you go. It's 50%. Since it's more than 1, it's an increase. Down here, how far is this from 1? 0.3. So you're 30%. Since it's less than 1, it's a decrease. That's a quick way you can evaluate these. All right, let's continue. Here's another one. Find the equation for the exponential function represented in the table below. So again, we talked about this. A is 15. We'll use this as our x. That is our y. So I have 18 equals 15 times b, which I don't know, to the first. So simply just divide both of these by 15. All right, do I leave that? Yeah, I left that as a decimal. So b equals 1.2. So here's your equation. A of t equals 15 times 1.2 to the t. What percent was f of x increasing or decreasing by? I'm not even going to use a formula now. We just talked about it. How far is this common ratio from 1? Well, 0.2. Okay, so 0.2 is what percent? 20%. And since it's more than 1, there's an increase, 20% increase. All right, so now we're going to get a little bit more complicated, but this is super important. An exponential function must be in the form a of t equals a times b to the t to determine if it's a growth or decay model. The exponent t must be by itself. So in this example, we just have to determine whether it's growth or decay. I don't even need to tell what the percent increase or decrease is. At first glance, you might think, oh, it's decay because I see a 0.6 in there. But notice, that exponent's not by itself. So what we have to do is we have to take the numeric part of that and bring it inside. So what you have to do first is you have to calculate 0.6 to the negative 2, and then just leave the t on the outside. Well, if we do that, 0.6 to the negative 2, throw it in your calculator, is 2.78. So this expression right here is exactly the same as this expression. Well, clearly you can see now, there's my t by itself. This is growth. So in this group of examples, we are just moving the exponent inside the parentheses. Okay, so this one here, b, will be 1/7 times 2 to the negative 3 to the x. So evaluate that. 2 to the negative 3 is 1/8. You can do it without a calculator even. So 1/8 right here is a decay. All right, letter C. All you have to move inside is this negative 1. All right, so that one would be 5 times 1/3 to the negative 1 to the t. Well, again, that one's easy to do without a calculator because the negative exponent, you just take the reciprocal of the base. So that's 5 times 3 to the t. Your common ratio is more than 1, so that is growth. And our last one, again, without a calculator, I can do this. Bring in the 1/2. So I have 2/3 times 49 to the 1/2 to the x. well, the 1/2 power is the same thing as the square root, so that's 2/3 times 7 to the x, and 7 is clearly more than 1, so that is also a growth. So something to be aware of now as these functions become a little bit more complex. You can't leave it like this. I only want to see the x, so any number that's attached to that exponent, you move inside the parentheses. Okay, wrap it up here. To the nearest 1/10 of a percent, find the percent increase, decrease for each one. So a little bit more involved than what we did the previous couple pages. I have to move that inside. Okay, so I don't really need to write the 2/3. I'm only concerned about the percent increase or decrease. But anyway, 16 to the 1/4 to the x. Well, that equals 16 to the 1/4 is the 4th root of 16 is 2. So here's something that's interesting. My percent increase is how far your common ratio is from 1. So you got to be careful here. That's not a 200% increase. That is a 100% increase. And if you get confused by that, just take an extra step and say, oh, let's just subtract 1 from it. Well, that's 1. 1 is 100%, and that'll be a 100% increase. Okay, so on the next one here, I've got to bring in that -3. So that's 1/2 times 3 to the -3 to the x. And since it wants it to the nearest 1/10 of a percent, I actually have to break out the calculator. 3 to the -3, which is 1/27. I got 0.037,037. And that would be to the x. So what I would do next is take 1 minus that. I want to figure out how far away that is from 1. And don't round until you get to your percent. So that would be 0.962963. So now, as a percent, you move this 2 places. 96 point all of this stuff. It says 1/10 of a percent. So if my decimal's here, that's a 9. That would go up to 3. So 96.3. 96.3% decrease, right? Because that's less than 1. That's what remains. That's a very, very small percentage that remains. So it kind of makes sense that you have this decrease. All right, letter C. Let's move this exponent inside. I can probably do this one without a calculator. So it's going to be 5 times 1/3 to the -2 to the t. Well, 1/3 to the -2, take the reciprocal of that base, that's 3. Square it, that's 9. That's 5 times 9 to the t. It's not 900%, remember. That's 800%. 9 minus 1 is 8. That's an 800% increase. And the last one, we're going to bring in the 2. So that's 4 times 0.6 squared on the inside to the t. 0.6 squared is 0.36 to the t. So that's going to be a decrease. How do you determine it? 1 minus 0.36. That's 0.64. So that will be a 64% decrease. All right, that concludes day 3. I know I threw a lot at you here. Please reach out if you have any questions as usual. Thanks a lot for watching, and we'll see you in class soon.